So today we're starting section 13. And again, I'm not really going by the topics in Algebra Nation. But if you need some extra resources, if you'll ask me what you're having struggles with, I can refer you to like the section in Algebra Nation that you should look at. So the whole section 13 is called trigonometry. And the topic we're doing today is called the unit circle, which I think on Algebra Nation, the unit circle is, that's not the unit Urkel, it's the unit circle. I think it's unit or topic 1 and 2 on Algebra Nation. All right, so before we get started, on the unit circle, which I passed that out to everybody, everybody's cut it out. I'm going to teach you how to fill in every single part of that unit circle that you have in front of you, okay? If you're going to pre-calculus, they're going to expect that you have that memorized, all right? I'm going to show you how to come up with the numbers. They're going to want you to memorize it because you're just going to have to know it just like that to solve problems quickly and in the time that they expect you to. But for our purposes, I'm going to teach you how to find each of those blanks, okay? But first I need to teach you some definitions. All right, an angle in the coordinate plane is in standard position when the vertex is at the origin and one ray is on the positive x-axis. The ray on the x-axis is the initial side of the angle the other ray is the terminal side of the angle. So I'm going to draw you a little diagram. So this whole thing, this is an angle in standard position. It said an angle's in standard position when the vertex is at the origin, which it is, here's the origin, The vertex is at the origin, and one ray is on the positive x-axis, which it is. The ray on the x-axis is called the initial side. So this part of the angle, this ray here, would be called the initial side. And the other ray of the angle is called the terminal side. So when I teach all about the unit circle, when we're measuring angles, one of the sides, the initial side, it always starts here, and then your angle will either open up counterclockwise or clockwise, okay? And we'll get to that later. If your angle opens counterclockwise, it's considered a positive angle, and if it opens clockwise, it's a negative angle. So one more little thing for me to write here. The measure of an angle in standard position is the amount of rotation from the initial side to the terminal side. So like the measure of this angle, if I were opening counterclockwise, well, we know from here to here is how many degrees? 90 degrees, that's a right angle, right? So from here all the way till this point is how many degrees? 180, straight lines, 180 degrees. And I'm assuming this angle looks about halfway between here, so that's another 45 degrees. So 90 plus 90 plus 45, that's probably a 225 degree angle. So if I were measuring from, if my angle was opening this way, that would be positive 225. If I start with my initial side, if my terminal side swung this way, when you go clockwise, that's a negative angle. So we would be negative 90 here, and then plus another 45, or minus 45, however you want to think about it. That would be a negative 135 degrees if we came this way. If my terminal side opened clockwise, negative 135. Okay? This is all going to be important when we get to the unit circle. And we need to write that down. The measure of an angle is positive when the rotation from the initial side to the terminal side is in the counterclockwise direction. the measure is negative, when the rotation is clockwise. So let me draw two little easy diagrams for you down there. So here's my terminal side, or I'm sorry, initial side. If my terminal side had a counterclockwise rotation, that would be, I'm estimating here, that would be positive 120 degrees. That's counterclockwise. Y'all know what that means, right? And then if your initial side's always going to be in the same place, it's on the positive x-axis. And then if we went clockwise, so my rotation is clockwise, that gives me negative 120 degrees. So it just depends on which way you're rotating, as if it's positive or negative. Okay? Do you have questions so far? Alright, so on page 199, we're going to glue in the unit circle. You can just put it right in the middle of the page. On page 199. Does everybody have this written down? Alright, 199. So on the circle, those little, if you'll look up here, those little things are like degrees. Those little circle things. So you write a degree, like if it was something that was 90 degrees, the degree would be to the right of it. Okay, so for this to be in the right place, that little degree would be to the right of a number. So if you have it upside down, you don't want the degree to be below the line. Okay, glue it in so the degree is above and to the right of those little lines. Okay, so the first thing we're going to do, we're going to fill in the degrees of the whole unit circle, okay? We have to fill in degrees, we have to fill in ordered pairs, and we have to fill in what's called radians, all right? So the first thing you need to know is that on a unit circle, the radius of a unit circle, every radius has a length of 1, okay? So y'all know what a radius is, right? Goes from the origin to the edge of the circle. So each one of these lines in the middle, on a unit circle, they all have a length of 1. Just 1 unit, all right? And a unit circle is basically split into 30 degrees, 45 degrees, 60 degrees, 90 degrees. So that's easy in that first quadrant to fill out the degrees, but then we got to do a little bit more work over here, okay? So first of all, right here we're at 0 degrees. And then we go up to 30 degrees, 45 degrees, 60 degrees, and 90 degrees. So that part's easy. So that next big jump, there was 30 degrees between this angle and this angle. Well, there's going to be 30 degrees here, 15, 15, 30 degrees. Okay, 30 degrees, 15, 15, 30 degrees. 30 degrees, 15, 15, 30 degrees. Does that make sense? So 90 plus 30 would be 120 degrees. Plus 15 degrees is 135 degrees. Plus another 15 degrees is 150 degrees. And then we already know a half of a circle, that's 180 degrees. But if you added 30 to that, you get 180, right? So then we have another 30 degree jump, so that's 210 degrees. A 15-degree jump puts you at 225 degrees. 15 more degrees, you're at 240 degrees. 30-degree jump, you're at 270 degrees, which y'all know 3/4 of the way around a circle is 270. 90, 180, 270. So then that next big jump's 30 degrees, so we're at 300. Plus 15 degrees, you're at 315 degrees. Plus another 15 degrees, you're at 330 degrees. And then if you make the full rotation, they didn't put a little spot for that, that would be 360 degrees. So you're at this point, you're either at 0 or 360. If your terminal side, your initial side and the terminal side, if the terminal side has not made any rotation, you're at 0. But if your terminal side has rotated all the way around, then you're at 360. So it just depends, okay? Is it laying flat or is it made the full circle? Does that make sense? Okay, so for each place on this unit circle, we have to find the ordered pair, and then we have to find how many radians it is. Do y'all have any clue what a radian is? Nope, probably not, okay? In geometry, you probably didn't talk about radians. Okay, so you kind of have to visualize this with me. So you know what a radius is, right? Okay, so in a unit circle, each radius has a measurement of 1 unit, okay? So a radian means if I pick this radius up, picking it up, and I'm laying it on the outside of the circle, all right? So here's 1 radius, I'm laying it on the outside of the circle. It means each arc is measured in radians. So of that radius, how many, like for this 30-degree angle, how many radians was that? Do you think that's going to make a whole radian? If I pick this radius up and laid it on the side, would this be a whole the same distance as from here to here? No. So what a radian is, it just tells you how many radii could you lay around the circle. That's what a radian is. Okay? So what we're going to put in these blanks is how many radians each one of those degrees is. Meaning, if I pick my radius up and laid it on the circle, how many of those radiuses did it take to get to that degree? And that's the best way I know to explain that. Okay? Think about if you took a little string, measured it out, and then laid it on the radius. Okay? How many would it take? Yes, ma'am?
Could you write a key in color code?
Write a key? What do you mean?
Like for the numbers, like so I don't get confused.
Well, on the next page, we're going to actually figure out all of the radians and organize it, and then we'll put it all on the next page. And I am going to color coordinate all of those from where I do the math to where I put them on my page. So maybe that'll help. Okay? And I am literally going to do the math for every single one of them. And so are you, so that you know how to do it. So that you know how to do it when you have to do it on your own. All right, so page 200. So also, all of those degrees that we filled in, they were all positive degrees. So that just means in that unit circle that we completed, the rotation was counterclockwise. But you could still have negative degrees. It just means your rotation will be going the other way, right? Okay. So now we will find out how many radians are in each degree. So we need to write that definition for a radian. A radian is the measure of a central angle. Remember from geometry, a central angle means you have an angle that is, the vertex is on the origin. That intercepts an arc with a length equal to the radius of a circle. Radians, comma, like degrees, comma, measure the amount of rotation from the initial side to the terminal side. So when we talk about 30 degrees is pi 6 radians, they're talking about the same angle. It's just in trig, you don't talk about degrees really, you talk about radians. Okay? They're still talking about the same angle measure. It's just in terms of radians instead of in terms of degrees. Okay, so they kind of mean the same thing. All right, and we already said this previously, but we didn't write it down. The unit circle has a radius of 1. And another important thing to note, which we already know this because you all had geometry and passed it, that the circumference of a circle is C equals 2 times pi times r, which in a unit circle, we know the radius is 1. So 2 times pi times 1 means that the circumference of a unit circle is just 2 pi. Because the radius is 1. All right, now let me show you how to convert degrees to radians. And there's a couple different ways that you can do this. This is just one. So if you see a formula that's different than this one, it's not that it's wrong or mine's wrong. There's just a couple different ways that you can that you're going to see it. Okay, but what we're going to use is this formula. So converting degrees to radians. So you do degree over 1 times pi over 180. All right, so we're going to start with that little 30-degree angle. We're going to convert it to radians. How many radians is 30 degrees? So like I said, I'm going to do these, I'm going to color coordinate them. So I'm going to do like that first quadrant in one color and the second quadrant in another color. And I'm going to have to write small because this is a lot of calculations, okay? So we have 30 degrees, because it's degree over 1 times pi over 180. So when we multiply fractions, we do numerator times numerator, and you don't want to change pi to 3.14, okay? You want it in terms of pi. So 30 times pi is 30 pi, and 1 times 180 is 180. And you want to leave it as a fraction, okay? Can we reduce 30 and 180? Does 30 go into 180 evenly? Yeah, how many times? 6 times. So 30 goes into 180 6 times. 30 goes into 30 once. So 1 times pi is pi, right? So if you go all the way around a circle, you've gone 2 pi times. That's in radians. When you see pi, that's in radians. So this is take a whole time around as pi divided by 6. It goes all the way around 2 times pi. So for radians, we have pi 6. And I'll go fill it in a minute once we do the first quadrant. So let's see what 45 degrees is. So 45 degrees divided by 1 times pi over 180. So 45 times pi is 45 pi. 1 times 180 is 180. Now you might not be able to reduce that all at once, but do you think 45 goes into 180 evenly? Yeah. 180 divided by 45, we get 4, right? So 45 goes into 45 once. So 1 times pi is 5. 45 goes into 180 4 times. So pi fourths. Let's try 60 degrees. So degrees divided by 1 times pi over 180. So that's 60 pi over 180, which is what? What is 60 over 180 reduced to? Pi over 3, right? 60 goes into 61, 60 goes into 183 times. So pi thirds. So let's go ahead and take and put this on the previous, on our unit circle. Don't put it in the ordered pair part. We're going to find that later. So 30 degrees is equivalent to pi over 6 radians. 45 degrees is pi over 4 radians. And 60 degrees is pi thirds radians. Let's go ahead and do the 90 degrees while we're at it. Yeah. So 90 divided by 1 times pi over 180. That's going to be 90 pi over 180, which is what? Pi over 2. So pi halves. Easy, right? All right, let's do the next section. And y'all can go ahead of me if you want to. I'm going kind of slow. You can speed it up. So I'll do 120 degrees over 1 times pi over 180 gives me 120 pi over 180. And I believe 60 goes in 120 and into 180. 60 goes in 120 twice, so that would be 2 pi. And 60 goes into 180 3 times, right? So you could either say 2/3 pi or 2 pi over 3. Either way, same thing. 135 degrees. And if anybody misses any of this, you can either watch the video later or you can borrow my book when we're finished. So that's 135 pi over 180. And I may have to reduce this a little bit at a time. Let's see, I know that 5 goes into both of them evenly. So if I divide by 5, I'll get 27 pi over 36. But can I reduce that more?
Yes.
Yeah. What goes in 27 and 36? 3. Anything higher? 9 does, right? So 9 goes into 27 3 times, and 9 goes into 36 4 times. Can I reduce it any further? No. So 3/4 pi, or 3 pi over 4. 150 degrees. So that's 150 pi over 180. And if I know they both have a 0, I can reduce by 10. So if I just reduce by 10 to start, that would give me 15 pi over 18. But can I reduce further? Yeah, what goes into 15 and 18? 3. 3 goes into 15 5 times. 3 goes into 18 6 times. Can I reduce further than that? No. And let me go ahead and do 180 degrees. I'm going to have to come up here. 180 over 1 times pi over 180. Right, that's just going to be pi, right? Because it's going to be 180 pi over 180, which will just reduce to pi. So 180 degrees is equal to pi radians. Well, that makes sense if the circumference 2 pi, right? If half is pi, then a whole time around is 2 pi. So 180 degrees is pi. And that makes sense for 90 degrees, it's just half of pi. All right, so let's fill this in. So 120 degrees was 2/3 pi, or 2 pi over 3. 135 degrees was 3 pi over 4. 150 degrees was 5 pi over 6. And 180 degrees is pi. Coolio. All right, I want y'all to do this next quadrant on your own. So do 210 degrees to 270 degrees. Do that quadrant on your own. Make sure you reduce. Just to make sure you're doing it right, how many radians is 210 degrees? Backwards. Should be 7 pi over 6. What did you get for 225 degrees? How many radians? Five pi over 4? Exactly. 240 degrees. 4 pi over 3 and 270 degrees. 3 pi over 2. Good. So let's fill that in. So 210 degrees was 7 pi over 6. 225 degrees was 5 pi over 4. 240 degrees was 4 pi over 3. And 270 degrees, 3 pi over 2. Any questions on how I came up with any of those? Same way we did before, just make sure you got to reduce all the way. Okay, go ahead and figure out where the rest of the unit circle. What did you get for 300 degrees? 5 pi over 3, good. How about 315 degrees? 7 pi over 4. 330 degrees? 11 pi over 6. And 360 degrees? But you already know what that one is, 'cause that's the circumference is 2 pi. So 300 degrees is 5 pi over 3. 315 degrees, 7 pi over 4. 330 degrees, 11 pi over 6. And 360 degrees is 2 pi. And for 0 degrees, the radians is just 0. Coolio. Okay. Now, that wasn't too bad, right? Formula, same time, just got to make sure we reduce. Now, figuring out these ordered pairs, that takes a little bit more work, okay? Do y'all remember in geometry when you learned about special right triangles, 30, 60, 90 degree triangles, and 45, 45, 90 triangles? No idea? All right, well, I'm going to teach you anyway. We need to know the relationships of those triangles to figure out all of the ordered pairs in the right triangle, okay? But before we do, the ordered pairs in the unit circle have signs just like on a regular graph that we do, okay? So everything in this first quadrant, are its x values positive or negative? Positive. What about its y values? Positive. So we know in this first quadrant, all of the ordered pairs, the x is going to be positive, the y is going to be positive. Because when we find these ordered pairs, they're all going to look positive when we find them because we're finding distances, which you'll understand in a minute. So we have to remember when we have to make them negative, okay? So in this second quadrant, are your x values positive or negative? The x's are negative and y's are positive. In this third quadrant over here, x's are and y's are negative. And in my fourth quadrant, x's are positive, y's are negative. Okay. If you don't pay attention to this part, I noticed several people are sleeping and have lost their points for the day. You're going to have no idea how to do this. And this will be on part of the quiz test, whatever we have on trigonometry, okay? So I would highly suggest that you pay attention to this. So on page 201, because you're going to have a quiz on the unit circle. I'm not going to have the whole unit circle blank, but just certain places on it, and you're going to have to fill out the parts, okay? With no notes and no help from me. So this page I'm gonna review important special right triangle relationships. Y'all should have learned this in geometry. Important special right triangle relationships. We have a long day in this class today. I know that. It's a lot of work, but you don't have homework, so that's the good news. Your grade for today will come from your class participation. Some of you are at a 50%. All right, let's start with the 30, 60, 90 degree triangle, okay? So try to get yours to look as much like mine as you can. So y'all know a 90-degree angle has to meet, it's perpendicular, right? Do you remember what the side directly across from the 90-degree angle is called? Nice. Hypotenuse. Y'all remember how to spell it? Hypotenuse. Hypotenuse. And you probably remember that the hypotenuse is the longest leg of a right triangle, right? Longest leg. Okay. The 30-degree angle is directly across from the shortest side of the right triangle. So if this is 90 degrees and this is 30 degrees, how many degrees must this be? 60 degrees. And that angle is directly across, this leg will be the middle length, okay? So directly across from the smallest angle will be your shortest leg. Directly across from 90 degrees will be your longest leg, and directly across from your middle degree angle will be the leg that's middle length, right? All right, this is a 30, 60, 90 triangle. Now, when you're dealing with a 30, 60, 90 triangle, your side lengths have relationships with each other. So if you just know one side of the triangle, the length of it, and you know what these relationships are, you could find all of the other sides and you don't even have to measure, okay? So we refer to the smallest side, we call it S. You want to think of it as smallest side. And the hypotenuse of a 30, 60, 90 triangle is always twice as long as the smallest side. So we would call it 2S. It's 2 times the length of the shortest side. And that middle leg is the length of the shortest side times the square root of 3. So say my shortest side had a length of 1 inch. Then the hypotenuse would be 2 inches, and this side would be 1 square root of 3, or just square root of 3, right? If this was 2 inches, that would be 4 inches, and that would be 2 square root of 3 inches. All right, just by knowing one length. So a 45, 45, 90 triangle, you want to make your legs look kind of, they need to be the same length as each other. Try your best. So on a 45, 45, 90, those legs have the same length. And then you know your hypotenuse is directly across from the 90-degree angle. And this is referred to as a 45, 45, 90. So the relationships we have on a 45, 45, 90, your legs, we just refer to them as S, or sometimes you'll see X, whatever, but they're both the same length, so they both are S. And to find the hypotenuse, you take the length of the leg and multiply it by the square root of 2. So that would be S square root 2. Notice one of them has a square root of 3, the other one has a square root of 2. This is how I remember, is it square root of 2 or square root of 3? I know that on the 30, 60, 90 triangle, all the legs, there's 3 different measurements, and on that one, square root of 3. On the 45, 45, 90, there are only 2 different measurements, right? Because these 2 legs are the same, and that's square root of 2. So that's how I remember which one's square root of 2 and which one's square root of 3. But you need to have that memorized, the relationship. All right. So when we're trying to figure out the ordered pairs on a unit circle, we use sine and cosine. All right, I don't know if y'all learned that in geometry, you were supposed to, but I'm going to reteach it like you've never seen it before. To find sine, S-I-N-E, comma, cosine, and tangent, of an angle and sine, cosine, and tangent, that's just ratios of the side lengths, okay? That's what it means. You're just taking ratios. The opposite over the adjacent, or a hypotenuse over the adjacent, or whatever it is. We can use SOHCAHTOA. SOHCAHTOA. Y'all ever heard of SOHCAHTOA? Yeah? Some teachers don't teach it using SOHCAHTOA. That's the easiest way for me to remember. If I'm looking for sine, how do I find it? Well, sine is opposite over hypotenuse. If I'm looking for cosine, how do I find it? Cosine is adjacent over hypotenuse. If I'm looking for tangent, how do I find it? Opposite over adjacent. We're going to write all that out, don't worry. But that's how I remember it. I have to literally write SOHCAHTOA on my paper, and then that helps me know what goes over what when I'm trying to find sine, cosine, or tangent, okay? SOHCAHTOA. So I'm going to write that big, SOHCAHTOA. And sometimes I like to do this thing where I say, when I say SOHCA, you say TOA. See, isn't that fun? Y'all thought math wasn't fun. Now you know you were wrong. I am weird. What of it? Alright, so for SO of SOHCAHTOA, the S is for sine. The O is for opposite. The H is for hypotenuse. I don't know why I rewrote the first letter, but I did it the first time, so I just continued. So if you want to find the sine of an angle, you do make a ratio, opposite over hypotenuse, of whatever angle you're talking about, okay? For CAH, the ca part, C is for cosine. If you want to find the cosine of an angle, you do adjacent over hypotenuse. And if you want to find the tangent of an angle, you do the opposite side over the adjacent side. So I'll write those out at the bottom. So for sine, and abbreviate. Abbreviation of sine is SIN instead of SINE. Sine equals opposite over hypotenuse. Cosine, the abbreviation is COS. Cosine is adjacent over hypotenuse. Tangent, the abbreviation is TAN, and that's opposite over adjacent. So we're going to find the ordered pairs for every degree or radian of that whole entire unit circle. And we don't have to use tangent in the unit circle. But for SOHCAHTOA, you have to write tangent down. And if it asks you to find a tangent, that's how you find it. But for the unit circle, we only need sine and cosine, okay? X comma y, the cosine is your x value, and the sine is your y value. So we're just going to be using cosine and sine to find the ordered pairs around the whole entire unit circle. And we won't be able to finish all of that today. Don't be sad. Page 202. Suppose an angle in standard position. Suppose an angle in standard position has measure, and this is a little symbol. It's kind of like O with a little loop through it. That's called theta. So that's kind of like whatever angle you're referring to, we call it theta, okay? The cosine of theta, and so we don't write the word out anymore, we just use the symbol. The cosine of theta is the x-coordinate of the point at which the terminal side got your phone out? You lying? Fibbing? Of the angle intersects the unit circle. The sine of theta is the y-coordinate. So we're going to start with 30 degrees. We have to know our 30, 60, 90 degree triangles. And we're going to find the cosine and sine of each angle the whole way around. Okay? And I'm going to make a circle every single time. A little circle. But not too small because you want to be able to read it, okay? My first angle measure, theta, is 30 degrees. And I want to find the ordered pair where they enter the circle. What's its x value? What's its y value? So you're finding the cosine, because that's the x, and the sine of theta. And you're like, well, that's not a triangle because two sides are straight, but the one side's the arc of a circle. That doesn't make a triangle. Correct. So what you do is, do I need to slow down? So what you're going to do is, whatever that point is that intersects the circle, you're going to draw a line straight down so that it forms a 90-degree angle. If your angle was all the way over here, like in the fourth quadrant, we would draw it straight up, okay? It needs to intersect that semicircle line. So if we know we drew these two lines so that they're perpendicular, that's the 90-degree line, right? Or 90-degree angle, not 90-degree line. So this angle must be the 60-degree angle. Where we are finding the cosine of whatever this angle is that's on the origin, that's what we're finding the cosine and the sine of the 30-degree angle, okay? So we're finding the cosine of 30 degrees and we're finding the sine of 30 degrees. That's my theta. That's the angle I'm referring to. Whichever angle is formed at the origin. Just forgot my dot. So, I always write my little SOHCAHTOA out. When I say SOHCAH, you say TOA. And then also what I want to do is I got to label my parts. Okay, so I know on a 30, 60, 90 triangle, I know my smallest side is X, and that's directly across from the smallest angle, right?
Excuse me.
Yes?
You have Taylor Petrovich?
I do.
Can you send her 2 pins, please, for checkout?
Sure.
Thank you.
You're welcome. I know my hypotenuse is 2 times the smallest side. And I know that this part of the triangle, the part directly across from the 60-degree angle, is, I used X's here, I used S on the previous page. It doesn't matter. Since I used X, I'll do S square root 3. Hope that didn't confuse anybody. You're welcome. Okay, so for cosine, that's the cut part, right? That's adjacent over hypotenuse. And we're talking about the 30-degree angle. So yeah, the hypotenuse is adjacent to the 30-degree angle, but it can't be, the hypotenuse can't be the hypotenuse leg and the adjacent leg both at once, okay? So your hypotenuse, the 2x, that's what would go in the denominator. And so this other leg that's adjacent to it, that would be your x divided by, or I'm sorry, x times the square root of 3. And then simplify that where you can. This x is not under a radical, this x is not under a radical. So could I reduce those? Yes, I could. So that would leave me with a square root of 3 over 2. I can't reduce 3 and 2, but say that was the square root of 6 over 2. Could you reduce those? Not if the 6 is under a radical and the 2 is not, okay? But regardless, I can't reduce 3 and 2 anyway. So the cosine would be square root of 3 over 2. So that's like my x value. That is the length of my x-axis, between here and here. Now I'm going to find the sine of theta. I'm referring to 30 degrees, so that's my theta. So for sine, I do opposite over hypotenuse. So I'm talking about the 30-degree angle. What leg is opposite of the 30-degree angle? X. And what is the length of the hypotenuse? 2x. Do my x's cancel? Yeah, so what's left in the numerator? 1, and the denominator? 2. So that ordered pair where this line intersects the x-axis, the x value is square root of 3 comma 2, the y value is 1/2. Okay? So let's go back over here. This is x is square root of 3 over 2. The y value is 1/2. And remember, it's cosine, comma, sine. That's your x value. And so right here on the x-axis, it's square root of 3, comma 2. On the y-axis, we're at 1/2. That's assuming the unit circle has a radius of 1, okay? Everybody cool with that so far? So we're going to do this all the way around because this stuff takes a little practice to kind of understand what you're doing, okay? The math part of it's easy. It's just making sure you get the right stuff in the right places. All right, so let's go to the 45-degree angle. I use either 30, 60, 90 triangles or 45, 45, 90 triangles and the whole thing, okay? So from here, go to the point where it intersects the circle and draw a line straight down to the radius. And that's going to be your 90-degree, that'll form your 90-degree angle. Which means obviously the other angle's 45 degrees, right? And mine looks very off. My whole drawing's off, so we kind of got to assume that it's 45, 45, 90, although you can look at it and tell that it's not exactly 45, 45, 90. So we're looking for this ordered pair. Cosine, comma, sine. My theta is 45 degrees. I know in a 45, 45 degree triangle, the two small sides we refer to as x or s. I said s on the previous page, whatever, the variable. And the hypotenuse is the length of the small side times the square root of 2, x square root of 2. And I'm finding the cosine of theta. Theta is this 45-degree angle right here. So I'm finding the cosine of 45 degrees and the sine of 45 degrees. So we know cosine's adjacent over hypotenuse. So looking at your angle here, what side length is adjacent to the 45-degree angle? Remember, the hypotenuse can be considered adjacent. Hypotenuse is only hypotenuse. So it's x, right? And the hypotenuse would be x square root 2. Now your x's will cancel out, so you'll just have 1 in the numerator and square root of 2 in the denominator. But do y'all recall that you can't have a square root in the denominator of a fraction? You can't leave a square root in the denominator. So you have to do what's called rationalize the denominator. So that means whatever the denominator is, multiply by a new fraction. It would be times the square root of 2 over the square root of 2. Because what's the square root of 2 times the square root of 2? It's the square root of 4. And what's the square root of 4? 2. So you just got rid of the radical in the denominator. And the numerator, what's 1 times the square root of 2? Just the square root of 2. And you can have a radical in the numerator of a fraction. You just can't have it in the denominator. And the reason it was okay to multiply by the square root of 2 divided by the square root of 2, well, isn't that the same thing as just multiplying by 1? Because square root of 2 divided by itself is 1, right? And you can multiply by 1 and not change the meaning. So that's rationalizing. Now, can we reduce this 2 and this 2? No, because the square root of 2 does not mean the number 2. It's 1 point something, and that does not cancel out with that 2, okay? So your cosine is square root of 2 over 2. Now to find the sine, sine is opposite over hypotenuse. So what leg is opposite of theta? X. And the hypotenuse is x over square root of 2. Well, that's exactly like what we did above, right? So we already know that's the same thing as square root of 2 over 2. And remember, everything in this quadrant, the x's are positive and the y's are positive. We have to be more careful about that when we're in the second quadrant, third quadrant, and the fourth quadrant. So on this one, the cosine and the sine are both square root of 2 over 2. All right, let's do that 60-degree circle. I'll get to the 90-degree circle and then we'll stop for today and then we'll figure out the rest next class. And you will see a pattern start to emerge. And I'm going to drop that line down to form that 90-degree angle. So we still have a 30, 60, 90 like we did in that first example, but in the first one our theta was 30 degrees. This time our theta is going to be 60 degrees. So we know this angle is 30, right? So we know in a 30, 60, 90 triangle, our smallest leg we refer to as x, and that's directly across from the smallest angle. Our hypotenuse is 2x. And that middle side is x square root 3. So we're finding the cosine and sine of 60 degrees this time. So cosine is adjacent over hypotenuse. So 60-degree angle, what leg is adjacent to it? X, and the hypotenuse is 2x, so that leaves me with 1/2. The sine is opposite over hypotenuse. What is opposite of theta? X square root of 3. And the hypotenuse is 2x. So my x's will reduce or cancel, and that leaves me with square root of 3 over 2. So my cosine, or my x value, is 1/2. So that means if this ordered pair right here has an x value of 1/2, the y value is square root of 3 over 2. Okay? And they're both positive. So 90 degrees, we don't really have to draw a triangle because, I mean, to find the ordered pair, what did we say the distance is of the radius? The radius is how long? 1, right? So this ordered pair right here has an x value of 0 and a y value of, from here to here, is 1. So that would be 0, 1. Let's go back over here. What is the x value of this point? Well, my x value is 1, because from here to here is 1 unit, right? And my y value is 0. At 180 degrees, this has an x value of, but it's not, it's -1, and a y value of 0. And this ordered pair has an x value of, x value 0, and a y value of -1. Well, we have 22 more minutes, so I can't stop this yet. Just let me do one more. One more. You don't have homework, so no huffing and puffing. We're going to get over into this quadrant, okay? You're going to see it's a little bit different. What are we going to do here? Because these aren't 30, 45, and 60 degrees, so how are we going to, well, you can't see that. So what are we going to do to make 30, 45, 30, 60, 90 triangles and 45, 45, 90 triangles? So let me show you one of those. Let's do page 203. Now again, like I said, in pre-calc, you're gonna have this whole thing memorized. You won't have time to, all these little things that we've worked out and shown our work on, you won't have time to do that in pre-calculus. You're gonna be expected to know each of these parts without working it out. So you're not gonna have to actually memorize it. All right, so next on our list, we are at the 120-degree angle. So it's 120 degrees from my initial side to my terminal side. Can you have a triangle with a 120-degree angle in it? Well, you can, but can you have a right triangle with a 120-degree angle in it? No. Okay, well, if we took, here's where we intersect, and we drew a line here to form a 90-degree angle, we could figure it out that way, okay? Because 120 degrees, we can't get a right triangle out of that. So if it's 120 degrees from here to here, then how many degrees is it from here to here? 60. Because you know a straight line's 180 degrees, right? So if we can just, we're still finding the same point on our circle. We're just having to use the other side of it to help us. Does that make sense? Yes, Ms. Fraley. Awesome. So 30, 60, 90-degree triangle. We know the smallest side we refer to as the X. Right? That'd be that little bottom part, just from here to here. The hypotenuse we call 2x, and the middle side is x square root 3. I should have just used x's on that first page since that's what I've been using every time. So my theta is 60 degrees. I'm finding the cosine and sine of this 60-degree angle. So cosine is adjacent over hypotenuse. Remember our signs over here too. Our x's are negative and our y's are positive. So we got to remember to add that in. Yeah. Did I do it wrong? Say it again. We're on the other side now. We did our 60-degree angle over here. We're doing 120 degrees. It's just we're having to use the back side of it to help us find it. The same location, we just can't actually use this part of the angle. So cosine of 60 degrees, what's adjacent to it? X, and the hypotenuse is 2x, so that gives us 1/2. So we know that's going to be negative 1/2 because our x values are negative in the second quadrant. And the sine is opposite over hypotenuse. So what leg is opposite of theta? X square root of 3 over the hypotenuse of 2x. My x's, I can reduce those because neither of them are under the radical. So that would give me square root of 3 over 2. And my y values in the second quadrant are positive. Only the x values are negative. So that's negative 1/2, comma, positive square root of 3 over 2. Y'all try to do the 135 on your own, and I promise this really is the last one. Try to do the 135 on your own. Hmm? I don't want you to follow a pattern. I want you to do the math. You'll see if it works out. There is a pattern, but I want you to be able to do the math because you're going to forget if you don't, and then memorize it. Did you find this already? And what did you get for sine? What'd you get? Okay. Anybody get the answer yet? What'd you get? Negative what? Very good. For her x value or cosine, she got negative square root of 2 over 2, comma, the sine or the y value is positive square root of 2 over 2, right? Because if you had a 135 degree angle, what's left to get to the 180 degrees is 45. So that will make a 45, 45, 90. I did cosine and sine. You end up with that radical in the denominator like we did on the previous page, so you have to rationalize, right? So make sure you go back to your unit circle. And for 135 degrees, it should be negative square root of 2 over 2, comma, square root of 2 over 2. Y'all starting to catch on? Not really. Okay, well, we got a whole bunch more to do. But we'll do that next class, okay?